Okay, so this is blast from the past number 8. And as you can see, it comes to us from exam 2, spring 2018. And it was problem 1. Okay. And again, it's similar to some of the problems you're doing now, homework 9. Okay, let's read it together. A right-handed circularly polarized plane wave at 1.575 gigahertz from a GPS satellite is incident on the Earth. Now, that's the actual frequency called the L1 band of a GPS satellite. The different bands, that's the most common band, L1 band. The Earth has a relative permittivity of epsilon equals 6, typical soil, and is taken as lossless, probably for the purposes of reflection coefficient. You don't have to worry too much about the loss of soil. Ocean water, that might be different, okay? But soil, probably if you take it as lossless. The angle of incidence is theta I equals 60 degrees. And the power density in the incident plane wave from the GPS satellite, which is orbiting at an altitude of 20,022 kilometers, is 10 to the minus 13th watts per square meter. Okay. And when we talk about antennas, it will become pretty clear how we can calculate something like the power density of the wave hitting the Earth from the GPS satellite. But anyway, that's what it comes out to be in this example. All right. So anyway, part A, calculate the power density in the reflected plane wave. B, calculate the percentage of the reflected power density that is TM polarized. And C, what would the angle of incidence have to be if we wanted no power to be reflected in the TM-Z polarization? Okay. All right, so part A, calculate the power density in the reflected plane wave. Now, here's the problem. Here's the geometry. So here's the Earth, 60-degree angle of incidence, right-handed circularly polarized wave coming in from the GPS satellite at 1.575 gigahertz, and then it's reflected. Okay. All righty. Part A, calculate the power density in the reflected plane wave. Okay. Now, I didn't give a whole lot of details here, but the first thing I'm doing is I'm just following the procedure that we talked about last time in the notes to get the reflection coefficients for TM and TE. So just to remind you, the reflection coefficient is Z2 minus Z1 over Z2 plus Z1, Z2 for the transmission line modeling the Earth, Z1 for modeling the air. And we had those formulas for the Z's. So TE is omega mu over KZ, TM is KZ omega epsilon. Remember what I'm talking about from last time? Okay, all right. So hopefully, and I invite you to go ahead and calculate these yourself just to verify that you get the same thing, okay? But anyway, so following the exact same thing I did in last time's example in the notes, we get the gamma TM and the gamma TE, okay? All right, now, part A is the power density in the reflected plane wave, okay? And I use the symbol PD, standing for power density watts per square meter in the reflected plane wave. In other words, in the wave coming off here. So remember, incident plane wave, 10 to the minus 13 watts per square meter. That was given. What is it in the reflected plane wave? Okay. All right. Now here's the equation I used. Let's see if we can understand it. Okay. So you got the incident power density, again, 10 to the minus 13 watts per square meter. Now remember that this is a right-handed circularly polarized plane wave coming in. Now that means it's got equal TM and TE components. Okay. Now, when we did circular polarization, at first, we had a wave going in the Z direction, so we would say equal X and Y components, right? But to be more general, for this wave going at this angle of incidence like this K vector, we would say equal TM and TE polarized parts. Equal magnitude and 90 degrees out of phase. We don't really care about the phase in this calculation, but we care about the fact that they're equal amplitude, okay? Now, because they're perpendicular like this, here's a wave coming in. It's got in the phasor domain, E like this coming in, right? Okay. And so if the total power density is 10 to the minus 13 watts per square meter, what's the power density going to be in TE part and TM part? Now, because these two waves are perpendicular like that, the E fields are perpendicular, you can just add the power density. Do the Poynting vector calculation like we did that if we have EX and EY, remember? So it has the magnitude of EX squared plus the magnitude of EY squared over 2 eta. So because the two E fields are perpendicular, total power density is just power density in TE plus power density of TM. Okay? So what's the power density in each one going to be? Can you tell me? If the total is 10 to the minus 13 watts per square meter coming in the right-handed wave, how much power density is going to be in its TE part? How much is going to be in its TM part? Half. Just half, right? Excuse me. Okay. So that's where the half is coming from. Incident power density times a half. That's how much is coming in TE and also TM. Now, how much power is being reflected, let's say in the TM case? Now, let me remind you that gamma TM or gamma TE is reflection coefficient for the field. Reflection coefficient for power is magnitude of gamma squared, right? Okay, so the power incident in TM polarization is P incident times a half. That's what's incident, and then multiplied by magnitude of gamma TM squared. So this term right here is the power density watts per square meter of the TM part of the wave that's being reflected. Does that make sense? And then do the same thing for this, gamma TE. So this times this is the watts per square meter in the TE part of the wave that's reflected, right? And then you add the two together, of course, you get the total power density watts per square meter that's being reflected off the Earth. Okay, does that make sense? Okay, and so anyway, you do that simple calculation using these values here, and it comes out to be this. So 10 to the minus 13th watts per square meter is incident, and about 2 times 10 to the minus 14th is being reflected, and of course the rest got transmitted into the soil, the Earth. Yeah.
Total power density.
That's what this is. This is the total power density in the reflected plane wave.
When you were saying like this term, when you did this, we're talking like you did incident power times 1/2 times gamma TM squared. That would give you the power density in the TM.
And the TM part of the reflected wave.
Okay, so how we get 7.
Yeah, so this is the power density in the TM part of the reflected wave. This times this is the power density in the TE part of the reflected wave. So the sum must be the total, right? Okay, okay. All right. Let's see, is it okay? Anybody else have any questions on part A? Okay, now notice that the reflection coefficients are both negative and pure real because of the, just like in the example in the class notes, because in this example, the Earth was taken to be lossless. No conductivity, real epsilon R, no polarization loss. So that's when your reflection coefficients are always going to come out real. If you remember, we did the reflection off the seawater, the gammas were complex, if you remember that. And that would be the case here too, if we had lossy Earth. But we're taking hypothetical lossless Earth, so we get real reflection coefficients. Okay. All right, so part B was calculate the percentage of the reflected power density that is in the TMZ polarization. So we're looking at the reflected wave now. We already know how much total power it has in it, and that's this number here, right? So that's the watts per square meter in the reflected wave. Now, if you just look at the reflected wave, what percentage of its power is in TM? That's what it's asking. Okay. Okay. So now you can put in P incident if you want in the numerator and the denominator in this formula. It doesn't really matter. It's just going to cancel out. So, but anyway, so the percent in the reflected wave, the percent of power in the TM wave would be, and again, you usually put P incident here and P incident here, but I just canceled it out, took a shortcut. Okay, but anyway, so P incident times 1/2 times magnitude of gamma TM squared. So that's the power in the reflected wave, that's TM, and the total power of the reflected wave is P incident times 1/2 times the sum, like I just showed you, like right here, right? So that's the denominator, and then the numerator is just the TM part. So in the reflected wave, TM power over total power in the reflected wave. And again, I cancel out the P incident. Okay, so it came out to be about 4%. 4%. So 4%. So in this reflected wave here, and we know it's carrying this amount of total power watts per square meter, and 4% of it, only 4% is TM. So about 96% of it is TE. Can you think of a physical law this relates to that we learned to last time? The TM part is so much weaker, right? Only 4% of the total power in the reflected wave is TM. Most of it is TE. What physical law relates to that we learned last time? That was one of the last things we did last time. What's that? Exactly, the booster angle, the booster angle. If this incident wave was coming in not at 60 degrees, but at the booster angle, how much power would be in the TM wave that gets reflected? Zero. Now, this is not at the booster angle, so there's some TM power, but it's only 4% of the total in the reflected wave, right? Okay. But anyway, part C was almost exactly that kind of thing there. Part C was, what would the angle of incidence have to be if we wanted no power to be reflected in the TM polarization? And like you just said, of course, that's the booster angle, right? So here's the formula. Now remember, the way we talked about booster angle in class and derived it, there's only an exact booster angle if it's lossless medium, right? So, but it is here. So just plug in, 6 over 1, take the inverse tangent. So about 68 degrees. So it wasn't terribly far from 60. And that's why only 4% of the power was TM, right? Yeah. Well, okay, now in this particular example, remember the upper region is air. So for air, epsilon r is 1, right? Or close enough. I mean, technically speaking, it's 1 for vacuum, but it's close enough for air. Yeah. I always assume it's 1 for air. Yeah, please.
Give us a question where it's like, for some reason, like if it's coming from water to dirt, like you'll specifically tell it's like it's coming from something.
Well, I think the problem would always tell you which region the wave is incident from. Yeah. And usually there'd be a figure to go along with it too. So it's here, it's pretty clear, right? It's coming from here. Yeah. Yeah. Yeah, I mean, it would be a strange example, but theoretically you could have a wave coming from inside the earth hitting the interface. That'd be pretty weird, but I guess you could have it theoretically. Okay. Okay, anything else? Yeah.
How do you determine if it's still a circular wave?
Oh, yeah, right. Okay, good question. Okay, so let's think about it a second. Okay, so in this case, it's right-handed circularly polarized coming in. So again, equal power densities and TM and TE, and that's why I put the half there, right? Okay. Now, look at the reflection coefficients. They're different. Okay, if they were the same, then the TM and TE waves would reflect equally, right? And then the reflected wave would stay circularly polarized, right? So is it going to stay circularly polarized here? No, of course not. It's going to be elliptical, right? It's going to be elliptical, right? Yeah. Okay. Now, because the two reflection coefficients are real numbers, it'll turn out that the two TM and TE waves maintain a 90 degrees phase difference. But they're not going to have equal amplitudes because of these different values here. Right. And notice the gamma TE is the bigger of the two. So therefore, the major axis of the polarization ellipse is going to be along the TE direction, not the TM direction. Yeah.
They were imaginary reflection coefficients, the magnitude.
I'm sorry, you're saying that these guys are imaginary?
Yeah.
Well, that's never going to happen for something like the Earth, of course. In fact, I'm not sure why you would get imaginary reflection coefficient. They can become complex, like in the lossy Earth, but that would be strange if they become pure imaginary.
It was a complex.
Yeah, a complex number. Now, this formula wouldn't change. This formula wouldn't change. Okay. These guys, just like an example we did in the class notes for the seawater, these would now become complex. And why? Why? Because the Z2 of the ocean is complex, right? And that's because ultimately it goes back to the Earth now has an epsilon C, right? Which is complex, right? And that makes the KZ, KZT, or KZ2 complex. So the Z2 becomes complex. But remember, the math is still perfectly valid, just like we did last time in the notes. Don't worry about that. I mean, it's a little bit of a pain on your calculator. You have to take a magnitude of a complex number, but it's not that bad. Yeah.
Gamma T and gamma TE were complex numbers. If we want to see if it becomes circular or not, or if it would stay elliptical, or yeah, would we take the magnitude of it and compare, or is it equal, or
And you're talking particular about the case if these were complex?
Yeah, yeah.
Okay, now, first off, they were complex, then, like I said a second ago, because they're both real here, the negative, but they're still real, so they have 0 degrees phase, or really 180, but because of that, it wouldn't disrupt the 90 degrees phase difference between the TM and TE reflected waves. When these guys become complex, that would disrupt that. So first of all, then the reflected TM and TE would not be exactly 90 degrees out of phase anymore. But even more important than that, though, even if these are complex, if they have a different magnitude, the reflected wave cannot be circular, right? Because the TM and TE are going to have different magnitudes. Because remember, CP requires both 90 degrees phase difference and equal magnitudes. So if you have equal powers coming in, and these two reflection coefficients have a different magnitude, that's going to tell you right there, it can't be circular, right? The reflected wave cannot be circular. Well, that's exactly what these numbers are here, right? Yeah. Yeah. Yeah.
Okay, thank you.
Yeah, I mean, whether they're complex or not, you need the magnitude of them squared, right? Yeah.
So it's the magnitude and the phase of the reflection coefficients, and they're complex.
Yeah, now in real life, the magnitude of gamma is never going to be equal to the magnitude of gamma E unless you have the special case where the wave is coming in exactly straight down perpendicular to the ocean or the earth. That's the one case where gamma TM is equal to gamma TE. If it's coming in at any angle, they're never going to be equal, never. So in real life, in almost any practical case, a reflected wave is not going to be circularly polarized anymore. That's what you have to live with. Yeah. But that's what happens in practical wireless systems. You know, once the GPS signal from the satellite reflects off that building or something and then comes to your cell phone antenna, it's not going to be CP anymore. Yeah. Okie doke. Anything else? Okay. Good. So hopefully that'll help you a little bit more for some of the homework problems you see there. All right, so picking back up with the notes here. Now, we almost finished notes 18, just a few last comments, and then we'll move on to notes 19 here. So we've already talked about the Brewster angle. Let me just pick back up by giving you a practical real-life illustration of when it could be useful. So remember, the Brewster angle again, like we just did a second ago, here's the formula. It's the angle for which there's no reflected TM power. All the TM just is transmitted through and none of it gets reflected. Okay, that's what the Brewster angle is. I'm sure you're all familiar with polarized sunglasses. So it's a practical real-world example of polarization in action here. So let's see what that means here. So here's sunlight coming down. Now, you may see a problem like this in the homework. So let me just point out that sunlight is what's called randomly polarized. Okay, now that means it's coming polarization all different directions and all different frequencies. But for modeling purposes, we can assume that it's two waves, one TM and one TE with equal powers, just like we do for circular polarization. Okay, it's not circular polarization, it's a random polarization, but with random polarization, you can make the same assumption. TM and TE equal powers. Okay, so keep that in mind when you do the homework problem. So here's sunlight coming in, the color-coded, I guess, TM in blue and TE in red coming off. And now what I'm calling glare is this blinding reflection that you would see if you look at the puddle of water from the sunlight coming down, hitting and going back to your eye. Or I guess the optical term is specular reflection. Remember, there's a law of reflection. So the wave coming in, reflected wave making equal angles to vertical, right? And if this is a pretty good reflecting puddle of water, you're going to see a blinding light when you look at it. And the purpose of the polarized sunglasses is to try to reduce that glare. Okay. Now, it's probably in real life, this sunlight is never going to be coming exactly at the Brewster angle. That would be pretty lucky, right? But hypothetically, that's the best case scenario. It's coming in exactly at the Brewster angle. So then there's no TM reflected, no blue here. So that the wave that's reflected is only TE. Okay. Now, the purpose of the polarizing lens here is as a filter. And it's a molecular fact of how the molecules work. But anyway, you can Google it if you want. But basically, it's a filter. So it blocks TE and it lets TM go through. Now, there is no TM coming from the water. There is no TM in the glare, right? Okay. So what's going to happen here is no glare gets through here, right? So the glare is perfectly TE, and this blocks TE, so there is no glare. Now, so you don't see a blinding light when you look at the puddle of water, at least if it's coming from a booster angle. Now, if there's some person over here or some building, some object you want to see, then probably the light coming from that person or that object is randomly polarized too, and this will block the TE part, but there's still going to be TM part because, you know, it's not reflecting off anything, right? So if some person or object over here is just reflecting light, probably maybe half of it will be blocked, and, you know, sunglasses would half of it go through. But that's what sunglasses are supposed to do anyway, right? Reduce the total amount of light getting through, right? So no big deal. But the important thing is here, it's going to block 100% of the glare if the glare is TE polarized. That makes sense? So it's kind of a neat application of polarization in action there. Okay. Here's some pictures just from Wikipedia. It says a building seen through polarized sunglasses. When you look at objects, I guess the message here is sometimes when you look at objects or building or anything, things can look a little bit different when you look at them through polarized lenses, because, you know, an object may be reflecting both TM and TE. When you look at it and you block one of them, it may look kind of different. Okay. And now people can take advantage of the fact that different polarizations can behave differently. So here's another picture from Wikipedia. And let's read it off together. Polarimetry is the measurement and interpretation of the polarization of transverse wave. In other words, you know, plane waves, most notably electromagnetic waves such as radio or light waves. Typically, polarimetry is done on electromagnetic waves that have traveled through or have been reflected, refracted, or diffracted by some material in order to characterize that object. Here's an example of a synthetic aperture radar image of Death Valley, California, artificially colored, but using polarimetry. So satellites are in space, and they have antenna arrays, and they send out a wave, which is essentially a plane wave. By the time it hits the Earth, it bounces off and is collected back by the satellite, and then we can process and interpret that data to image the Earth. Okay. Now, a lot of times the satellites are what's called dual polarized. The satellite antennas are what's called dual polarized. In other words, they can transmit what they call H-pole or V-pole, horizontal polarization or vertical polarization. And often these two polarizations are different frequency bands too, to avoid mutual coupling between the circuitry and that sends out the waves. But anyway, so if you send out two different polarizations, horizontal and vertical, it gives you more degrees of freedom. And sometimes the image of the Earth might look different under horizontal polarization or vertical polarization. And people can take advantage of that. They compare with the images that they see with different polarizations and get more information about the Earth than just one polarization. So that's kind of what polarimetry is all about. Okay. You might want to also Google remote sensing. That's where you're using satellites in space to kind of look down on the Earth and kind of look at the terrain, see the moisture content here on the Earth. There are all kinds of neat things here if you want to know more about it. Okay. All right. So people take advantage of polarization, definitely. A lot of antennas have different polarizations for that reason. So the users had the option of doing like horizontal polarization or vertical polarization. And I think I mentioned this one day, but like another example is like the base station antennas for your cell phones. So the base station antennas most typically they transmit and receive in what's called dual slant 5 polarization. If you open up like a housing and you look at the antennas on a base station tower, you'll see a typical array of dipole antennas, and there'll be one like this. Say it's 45 degrees from vertical, right? It's called slant 45. Not horizontal, not vertical, 45. And then, so one antenna that looks like this, and the other antenna that looks like this, and an array of these, right? So slant 45 polarization. And that gives what's called, I think I mentioned this word before, diversity. And so they can take whichever signal is the strongest coming from this pair, right? And so that's what's called diversity, taking advantage of different polarizations to increase the signal strength. Okay. All right. So anyway, any questions on this before I move on? Yeah. It varies, but definitely the most common polarization for satellites is circular polarization, just like GPS. Yeah, I'm not saying every satellite is circularly polarized. You'll find some, I think, that are linearly polarized, but the vast majority are circularly polarized, right? And that's part of the reason I mentioned the Faraday rotation effect. When a wave goes through the ionosphere as a satellite, wave will, the ionosphere will rotate the polarization. And how much depends on the frequency and the thickness of the ionosphere, which depends on the time of day and various things like that. So to be really safe, they like to use circular polarization. Yeah. Okay, anything else? Okay, very good. Oh, ready? Let's see. Let's move on here. If it'll let me. Okay, so now we kind of change gears in the course. Now we have two topics left. Each one is not too long of a topic, but we have two topics left in this course. So one is called waveguides and one is called antennas. Okay, and that'll be the very last topic. Okay, I think each one will take probably 2 class periods, probably. That's my guess. Okay. So anyway, let's go to, so waveguide topic is 2 sets of notes, notes 19 and notes 20. Okay. Okay. Now, this is kind of a qualitative set of notes. It gives us qualitative discussion of different waveguiding structures, but then there's a little bit of math too that we'll see eventually. Now, the title is Waveguiding Structures. And here are some examples of waveguiding structures, the good old coax, fiber optic guides. And this is going to be the subject of notes 20, what we call the rectangular waveguide, the rectangular pipe, which is used to carry electromagnetic waves in it. Okay, it's called a waveguide, rectangular waveguide. Okay, all right. Now, waveguiding structure, and that's the title here, waveguiding structure. A waveguiding structure is simply one that carries a signal or power from one point to another without having energy escape. In a wireless system with antennas, energy is going all over the place, right? And there's Steve antennas picking up part of it. But a waveguiding structure channels the energy, and ideally nothing escapes. Okay, so there's 3 types of waveguiding structures commonly used. We already know about the first one, transmission lines. Of course, the coax is the most common of these. And you can also have like twin lead, but this is the most, or twisted pair, which is a version of that. But anyway, coax is the most common. Fiber optic guides, I'll say more about that in a minute, where a dielectric rod basically is used to carry a signal, but at optical frequencies usually. And then waveguides, which is a hollow pipe of metal, the most common one. They can be different shapes, but the most common one is the rectangular one here. So again, rectangular waveguide, subject of notes 20. Okay. Now, first of all, don't get confused in the terminology. Okay. So when I say waveguiding structure, I'm defining it right here. A waveguiding structure could be any one of these 3. Something that's carrying a signal, forcing it to go from point A to point B, right? That's a waveguiding structure. A waveguide is going to have a more precise meaning, and it means this thing right here, a hollow pipe of metal being used to carry energy or a signal. Okay, so that's the terminology. And of course, all waveguiding systems are an alternative to a wireless system, obviously using antennas. Okay, so again, most common ones here, transmission lines, fiber optic guides, waveguides, or hollow pipes of metal. Now, let's go over, I think this is good for us, let's go over a qualitative discussion of the properties and the pros and cons of these 3 systems here. Okay, some of it's a repeat, of course, from what we've already done earlier in the semester, but it's probably a good summary of all of this. So transmission lines. First of all, what is a transmission line? It's 2 conductors running parallel. Of course, one could be inside the other one, like a coax or twin lead. Now, what are some of the properties? You can propagate a signal at any frequency in theory, even down to, kilohertz or really, really low, or up to very high frequencies in principle. Okay. What's the disadvantage of a transmission line? It becomes very lossy at high frequencies, right? Because the R and G getting bigger, right? It can handle low or moderate amounts of power. Okay, you don't worry about power when you're just carrying a signal from point A to point B, like you might have in the electronics lab or something like that. But if you want to handle a lot of power, that's a different story. Okay, and I think I mentioned this one day, but the fatter the coax, the bigger it is, the more power it can handle. Okay, so that's why these cell phone towers have these big fat coaxes running up and down them. Okay, it has signal distortion if there's loss present. In the real world, there always will. So you might remember that if it's lossless and you don't have any R and G, then the wave does not distort. Okay, there's no distortion, as we call it, because there's no dispersion, which means the phase velocity is independent of frequency. We talked about that in the past. So if you send a nice rectangular pulse at the input, it's going to stay a nice rectangular pulse down the transmission line. Now, in the real world, because of the R and the G, that's not exactly going to happen. And it's worse for some systems like others. Like I showed you that microstrip, example from microwave engineering class. The microstrip line is a notorious one for really distorting signals. Something like coax, okay, not so bad, but any transmission line will do it to some extent. It gets worse at high frequency. Okay, may or may not be immune to interference. That depends on the type. The coax is immune because it's what we call a shielded transmission line. As long as that shield is thick compared to a skin depth, nothing can escape or penetrate from the outside, right? But this is not quite true for twin wave. We talked about that before, so just want to remind you. Now, we haven't really talked about this before, but we'll visit this soon. One way that people characterize a transmission line wave is to call it a TEMZ wave. We already heard what TE and TM mean, right? When we're plane wave discussion. This is TEM, both TE and TM. So if it's TE, what does that mean? EZ is 0. If it's TM, what does that mean? HZ is 0. What does TEM mean? Both EZ and HZ are 0. Okay, so that's like a mathematical property that we'll prove before too long here. That if it's a TEMZ wave, meaning HZ and EZ and HZ are 0, that's the type of wave, as we'll prove, that really is a transmission line wave. So all transmission line waves are basically TEMZ, which means they have neither EZ or HZ. Or another way of saying it is if I take any kind of a transmission like the coax, and I just take a cross section of it, you can call that the XY plane if you want. If I take a cross section of it, the E and H vectors stay in that plane. Okay, like the E vector will be in the radial direction, going from the inner conductor to the outer conductor, and the H will be in what we call the phi direction, going around like this, circulating around inside, but neither E or H will have a Z component. All transmission waves are of that kind, TEMZ, okay? We already know this formula for gamma, or I convert it to KZ if you like. And we also know that if it's lossless, we have no R and G, and this simplifies to KZ, which is minus J gamma, is omega times the square root of LC, but LC is mu epsilon, and therefore for a lossless transmission line, KZ is a real number, which is just K of the material, K0 squared mu epsilon R. It gets more complicated when you have R and G. That's when you have a beta minus J alpha. Of course, that could be important for dB calculations, right? But anyway, okay, so that's a transmission line. Here's a summary of some of the properties of a fiber optic guide, which is basically a dielectric rod. Okay, so thin that it's flexible, but it's a dielectric rod. Now, this is just a pretty picture of some dielectric rods, carrying light and making a pretty little artistic display here. But when you buy a real fiber optic cable, it's going to look something like this. And you have not only the rod, which is called the core, but there's other layers surrounding, like the cladding and the buffer and the final jacket for protection. But the important thing in terms of the operating principle is that it's a dielectric rod surrounded by a lower epsilon material. If it's a rod by itself, it'd be surrounded by air. It's not really surrounded by air in a real one because it's got this thing called the cladding, right? The cladding still has a lower epsilon than the core. Okay. Anyway, so it's a rod, not the rod. Just like a transmission line, in principle, it can propagate a signal at any frequency. It can be made very low loss. The main reason is because it's pure dielectric and it has no metal. Okay. Now, also, what's very important is that the manufacturers have gotten really good at making these out of very low loss glass materials. So the loss tangent of the dielectric is very, very low. No metal plus very low loss tangent for the dielectric. So those two together are why it's a really low loss system. Okay. Didn't always used to be that way, but now in modern times it is. And in modern times, the fiber optic guide is much lower loss than a coax or something. It has minimal signal distortion, right? Usually not very much. Very immune to interference, and that's because of the internal reflection effect, which I'll explain in a second. Now, it's definitely not suitable for high power. It's only used for signal propagation, not for power flow. Coax can be used for either one, but this is only used for sending a signal from point A to point B, not to transmit power. It's from a mathematical point of view, it's more complicated to analyze this kind of structure than any other kind of structure because the wave has both EZ and HZ components. It's the opposite of TEMZ. A transmission line wave, like a coax wave, is TEMZ, neither EZ nor HZ. This has both, and therefore people call it a hybrid mode. Because it's more complicated to analyze, I'm not even going to attempt to do it. If you took one of the graduate EM courses, like the one called 6041, we go into details analyzing this stuff, but we won't attempt to do that here. It involves Bessel functions and that kind of stuff. Okay, anyway, now let me say a few more comments. There are two types of fiber optic guides. So if you ever hear this term, these terms, it's good to know what they mean. So there's single mode fiber and there's multi-mode fiber. Now, single mode fiber is operating at a frequency where the fiber diameter is on the order of a wavelength or smaller than a wavelength. Okay, so, and it carries, because the fiber dimension is comparable to a wavelength, it carries a single mode. Now that might make more sense after we talk about the rectangular waveguide. We'll see that the rectangular waveguide can carry different modes, and we normally restrict the frequency that only one of them, the TE10 mode, operates, but it's kind of similar principle. We want a single mode going down the structure, and that means the fiber is very small so that the diameter is on the order of the wavelength. Now that's the highest quality fiber, and it has the lowest type of loss in dB per meter. Okay, but then there's the multi-mode fiber, which has a diameter that's maybe 10 times larger or something. So the diameter might be 10 wavelengths or something like that. And it's lossier, okay, but it's a cheaper type of fiber. Okay, and it operates on a different principle. It operates on the principle of total internal reflection, in other words, a critical angle effect. Okay, now because we talked about the critical angle effect, let's go ahead in a little bit more detail, because I think you can understand everything about it now. Here's from a Wikipedia page. So basically, think of a beam of light. Now remember, all our theory, like I mentioned, is based on plane waves, not beams, not narrow beams. But again, this is optical frequency. So even though this narrow beam, which is 1 millimeter wide, might still be 1,000 wavelengths, right? So the plane wave reflection theory still works pretty darn good, actually. Okay, so visualize, if you would then, this beam coming along here, and it's bouncing around internally at an angle theta from vertical. And remember, if you go this way from inside the rod, and then there's air out here, this is where the critical angle effect applies, right? Going from denser to less dense. So there's a critical angle here. Now, what if this angle theta is greater than the critical angle? This beam is going to be reflected here. And you remember what happens if you round the critical angle? 100% of the power gets reflected, right? Remember that? Now, let me remind you, does it mean there's no fields out here? There's that thing called alpha ZT in the notes. And it says that the fields outside in the air region are decaying exponentially, but at optical frequencies, that's very darn quick. You know, there'd be a tiny layer in the air region where you could measure some fields, but they're decaying exponentially fast in the air region. That layer where you can observe those fields might be just microns thick. So you're not going to work, and that's one of the reasons why you have that buffer layer, right? The wave has a time to totally attenuate before it reaches the outside of the cable. But anyway, if 100% of the power is reflected, then it's kind of neat, because this beam could just keep bouncing back and forth all day long, and it stays inside the fiber, right? So none of it escapes here, right? If you weren't beyond the critical angle, then there's going to be reflection coefficient and transmission coefficient, and the reflection coefficient would not have unity magnitude. It'll be like 90% power reflected or something, but 100% gets reflected now because you're beyond the critical angle. So it's pretty neat. Now, in this Wikipedia experiment, somebody has taken some kind of a glass or plastic rod, and it looks like they're using some kind of laser pointer or something that's trying to, probably a green laser, I guess, and shine it in there. And you can indeed see the laser beam bouncing around, staying inside, right? It's exactly the principle that these things operate on. So that's the multi-mode type of fiber, okay? This is a little bit more of an elaboration, but you know, not quite as important, but maybe it's interesting to you. So let me kind of go over it. Here's the same experiment. Okay, here's a laser being shown in. Now, there's a maximum angle called theta max from horizontal here, at which you can shine this laser in. Okay, so as long as you're less than theta max, this is what the picture is going to look like. The laser beam stays inside and bounces around forever. Okay, if you come in greater than theta max, then the beam is going to partially transmit through, and every time it bounces around, you'll have some leakage to the outside world, and that's no good, right? Okay, so you want to shine in the laser at an angle theta less than theta max. Okay, now let's see if we can figure out what theta max is from our knowledge of what we talked about before. Okay, so at theta max, the laser beam is coming in like this. It's being bent towards the normal, right? Because this is a denser region than air. It's coming along here. And then once it's inside, this is the critical point where this is the critical angle now, critical angle. So then, if you remember critical angle, when it comes here and goes to the less dense air region, it's skimming along perfectly horizontal. So that's the threshold, right? That's the threshold. You don't want this to happen. You want it to be reflected on the inside. And this is what you don't want on the outside. The boundary between the two is the critical angle like this. Okay, so this is the picture that corresponds to theta max, where the final beam is just on the border between escaping and being reflected back. Okay, now let's look at the critical angle here for a second. I'll apply Snell's law. So n rod, end of the rod, square root of epsilon r of the rod, times sine of the critical angle is n of the outside air region times sine of its angle with vertical. And because you're at the critical angle, of course, that's going to be, right angle here. So 90 degrees, sine of 90 is 1, and n of air is 1. So the whole thing is 1. Okay, so then just take n rod across and take the inverse sine. And so if you give me the epsilon r of the rod, and therefore n rod, I can calculate now the critical angle. So that's the first step in this calculation. I'm trying to get theta max, but this is the first step in the calculation. I've got theta c here, okay? All right, now let's look over here at this picture at the left end of the rod and look at the beam coming into the rod from the air region. Okay, I'll apply Snell's law one more time. So n air times sine of the angle, which I'm now calling n theta max, is equal to n rod times sine of what? Sine of this angle, right? Now, what the heck is this angle? Well, if you look at this is the right triangle here. Look at this right triangle. Okay, so this angle here is 90 degrees minus this one, right? So pi over 2 minus theta c. Now, sine of pi over 2 minus something is cosine. So hence this equation, and then n air is 1 again, right? So this equation reduces down to this. Now, remember, I've already calculated theta c first. So that's known, and now I can calculate theta max, right? So it's kind of neat. Applying Snell's law twice, we can calculate theta max. And this is the maximum, what you might call acceptance angle. Maximum angle at which you can shine the laser beam in so that the laser beam is then trapped inside the rod. Kind of neat. Okay. All right. Well, anyway, any questions though? Okay. All right. Now, finally, waveguides. Remember, the word waveguide means hollow pipe of metal being used to transmit an electromagnetic wave. It may seem kind of surprising that a hollow pipe of metal can be used to do that. A transmission line requires 2 conductors, right? But that's a TEM mode. But a hollow pipe can also be used to transmit an electromagnetic signal, and that's, again, the entire subject of notes 20. Okay, anyway, but let me go over a few qualitative properties. It's a single hollow pipe of metal, of course, with rectangular being the most common shape, that could be filled with a material, but in the real world, most of them are just left hollow, in other words, filled with air. Now, here's the main property that we'll see soon. It can only propagate a signal at a high enough frequency so that you're above what's called the critical frequency, or the cutoff frequency. Now, what is that? We'll get to that before too long. But every waveguide, depending on the dimensions, has a cutoff frequency. So it cannot propagate down to arbitrary low frequency. Now, if you take a typical waveguide that may be, inch across or a couple inches across, something like this, typical cutoff frequency is going to be the order of, a couple gigahertz or something like that. Okay, very typical. So if you want to propagate a low frequency signal, like let's say, 100 megahertz or 10 megahertz, why the waveguide has to be the size of this room. Okay, so it's not going to be practical. So that's why, as opposed to transmission lines, you're only going to see waveguides being used at microwave frequencies and above. Okay. This is called the width. In the x direction, the long direction is called the width. The width A must be at least 1/2 of a wavelength, lambda d, in order to be above the cutoff frequency. That's one way to think about it. It has a lot of signal distortion, even if it's lossless, and that's because of the property of the waveguide modes. We'll get to that later. It's just like the coax, it's immune to interference because it's a closed pipe of metal. Here's one reason why we like waveguides. It can handle large amounts of power, huge amounts of power. Okay. The only thing that limits it is because eventually you have such a high power signal going in it that the electric field becomes so strong inside of it that it exceeds the dielectric breakdown of air, which is about 3 million volts per meter, and the air ionizes and breaks down. Okay, that's what really limits it. That's a huge amount of power. So these things can carry gigawatts, huge amounts of power. Okay. Now here's some pictures. Waveguides are almost always used inside microwave ovens, although you probably can't see it unless you take one apart, but there's the waveguide for a microwave oven. You've got a high power device called the magnetron that produces the high power microwave signal at 2.45 gigahertz. That's the frequency they operate out the microwave oven. And the rectangular waveguide carries the high power signal from the magnetron into the oven cavity where your food is, right? So it's a rectangular waveguide being used to do that, okay, because they really want high power. Here's an example of what you might call waveguide plumbing, where rectangular waveguide is being used to go around like this. And this is coming from some building, probably some kind of transmit, a relay station or something. So there's some building in here that's amplifying a signal probably. I'm just guessing, I don't know, but then the signal's being, high power signal after being amplified is being pumped back into a transmitting antenna here on this tower. It's probably what it is, but I'm not 100% sure. Okay. Now, so and waveguides are used in almost all high power like radar applications. I mean, radar is where you really need a huge high power signal. And so, because the wave has to come from the radar antenna, hit the aircraft or whatever, and bounce all the way back, right? And so the higher power signal, the better. And oftentimes those high power radar antennas, like on Navy ships and whatever, they can transmit at gigawatt levels, enormous amounts of power. So you're not going to feed those things with coax. Okay, you're going to feed them with waveguides. They need the enormous amount of power. Also, a waveguide has lower loss compared to any type of transmission line. Okay, it doesn't have low loss compared to a fiber optic cable, but you're not going to power radar with fiber optic, right? So it's not a fair comparison. But the reason it has low loss is because it's a hollow pipe like this. And so we'll talk about what the field looks like before too long inside, but it's kind of spread out more or less, not exactly evenly, it's like a sine function, but it's spread out across the cross section. And that's what you like for high power. You want the pointing vector to be as evenly distributed across the cross section as possible. Now, what's going to happen in something like a coax? Let's go back to the coax just for a second. Okay. So you've got an inner conductor and an outer conductor. They're both carrying equal and opposite currents. So this one here, the skinny little wire, is going to be the one where it has a huge current density, right? Huge current density. And that's one that's also going to have a lot of high charge on it, surface charge density, very strong electric field around it. Okay. So if you try to pump more and more power through the coax, where's the electric field going to be the strongest? Right close to the inner wire. Okay. And because if that wire is skinny, then there could be a huge field there. So you don't have to pump too much power down the coax before the electric field gets so strong near that skinny wire that the dielectric starts breaking down. Okay. And because of the really high surface currents there, it's got a huge amount of loss compared to the waveguide because the surface current is so high. Surface current is what really gives you loss because of that effect called surface resistance that we talked about, the RS. But if you can spread out the field as evenly as possible here, then that means that surface current density is more uniform around the boundary and not so concentrated in one area, and that's good for lowering the loss. So distributing the fields throughout this cross-section allows you to transmit more power for a breakdown, and it also says it's going to be lower loss, less dB per meter. And that's good for high-power radar applications. You don't want to waste power, right? You want all the power to go through, and you don't want dielectric breakdown. Okay. Well, I should have gone to this figure first. So this slide is just illustrating what I just said a second ago. So again, here's the field inside the waveguide. Here's the field in the coax. Again, very, very concentrated near the inner wire. Okay. So that's what's going to limit the amount of power it can handle. That's what's going to give you more loss. Okay. Yeah. Okay, that's a good question. Very good question. Thanks for asking that. Okay, first of all, let me say that distortion is something that's of interest for communication people, right? So when you're transmitting a signal from point A to point B, that's when you're worried about distortion. You're not really worried about that for power applications, right? So for example, nobody cares about signal distortion in your microwave oven. There's no, you're not carrying information. You're just transmitting a single frequency, 2.45 gigahertz signal from the magnetron into the oven, and you don't care what happens. You don't care, right? As long as the power gets there, right? There's no signal, there's no modulation, right?
You just want to get them.
You just want that one wave to get there, right? Yeah. Now, radar is really high power. And yeah, on radar, you're worried about distortion. But remember, the radar signal is going through air, hitting off the aircraft and bouncing back. Air does not distort, right? So you're good with the radar. Yeah. Okay. Now, a few more comments about the waveguide. Again, it's much more details in notes 20. But I'm just giving you, I'm kind of giving away what's going to happen here. Now, here's the formula for the wave number, KZ, of a wave going down a rectangular waveguide or any kind of waveguide. So notice it's a square, and we'll derive it later, square root of k squared minus kc squared. K is the usual k for whatever materials inside the waveguide. Usually they're hollow, so usually k is k0. And then this kc is something called the cutoff wave number. Now, it depends on the dimensions of the waveguide, okay, and the mode you're operating in. For the rectangular waveguide, operating what's called the dominant TE10 mode, which is usually what we do for rectangular waveguide, Kc turns out to be, as we'll derive later, the simple number pi over A. Now, remember, A is just this longer dimension of the rectangular waveguide, what we call the X dimension. B is the shorter dimension, okay? That's the notation. So Kc, as we'll prove later, just comes out to be pi over A. So that's what goes in here, okay? K, as you can see, so it's a fixed number. And K, the usual K, usually K0, is just, of course, proportional to frequency, right? So just use your imagination. You know, Kc is a fixed number here, and Kc is proportional to frequency. So obviously, if you're at a low enough frequency, this number is less than this number, you're taking the square root of a negative number. If you're at high enough frequency, K squared is bigger than this number, and you're taking the square root of a positive number, right? Right at the boundary, Kc is equal to K is equal to Kc, you're taking the square root of 0, right? You're going to get 0. So that leads to a very interesting effect in a rectangular waveguide. There's a frequency, as I mentioned, called a cutoff frequency, above which the mode can propagate, and below which it cannot. Okay? And so the cutoff frequency is the frequency when you're right at the boundary where K is equal to Kc. You see that? So if you're higher than the cutoff frequency, this will be bigger than Kc. If you're lower than the cutoff frequency, this will be less than Kc. Now, here's a little bit more of a mathematical elaboration. So if you're above the cutoff frequency, this is bigger than this. You're taking the square root of a positive number. So I can just put the usual radical sign here, the usual principal square root. Remember what that means? Like radical square root of 4 is plus 2, right? Not negative 2, right? Anyway, so you take the square root of a positive number, you get a real positive number. So Kz is what you might as well just call beta, like on a transmission line. In general, Kz is beta minus J alpha, if you remember. Remember, gamma is alpha plus J beta. Kz is beta minus J alpha. So if you have a waveguide, you're above the cutoff frequency, Kz will just be a real number, you can call it beta. If you're below the cutoff frequency, this becomes a negative number. You're taking the square root of a negative number. Now I'm going to factor out a minus sign and reverse the order here. So now this one's bigger than this one, right? And I factor out the square root of -1. And you might ask, why did I call the square root of -1 minus J? Why didn't I call it plus J, which is the right choice? Wherever I talked about that in the past, the physical choice is the one where the wave is decaying, not growing, right? So it's got to be minus J. Now, you can call it minus J alpha if you want, right? Minus J alpha. So this term, this square root term by itself would be called alpha. The Nepers per meter attenuation of the wave as it goes down the waveguide. And it's like the critical angle effect. You know, you might say to yourself, what the heck? There's no loss. This could be a perfectly lossless waveguide, and the wave is attenuating? It's got an alpha? Why? It's like the critical angle effect. It's what we call evanescence. Okay, so you can have a wave that decays exponentially, even though there's no loss. That's possible. It's called evanescence. Okay, so it's really interesting that in a rectangular waveguide, you get this very important frequency called a cutoff frequency. Above it, this TE10 mode can propagate beautifully. Below it, it'll just attenuate and it's useless. Right? Okay, wait, before I forget this time, let me go ahead and get this going here. Now, let me get a little bit mathematical here, and we'll do more notes 20, but let me give a few mathematical properties here that'll be useful for understanding waveguides. Okay. Now, I'm going to give you this, it's called a statement, or you can call it a guided wave theorem. When microwave people study guided wave structures, they really like this theorem because it's very useful, because what it says, well, okay, let's just read it off. Now remember, in an electromagnetic field, there's 6 components, because there's 3 for E and 3 for H, right? In the phasor domain, EX, EY, EZ, and same thing for H, right? There's 6 of them, right? Okay. Now, the statement says, or the theorem says, all 6 field components of a guided wave can be expressed in terms of just 2 of them, EZ and HZ. What's important about the Z direction? That's the direction the wave is going in. Could be a coax, it could be a rectangular waveguide, it could be a fiber optic guide. It's running in the Z direction. That's what Z means. So all of the field components can be expressed in terms of EZ and HZ, as long as it's a guided wave. And what does a guided wave mean? The most general definition of a guided wave is that your E and H vectors have this mathematical form. E0, H0 means what you're doing is you're just really, well, you can think of it as being evaluating the field as equals 0. The 0 subscript means evaluated as equals 0, okay? So it has no Z in it. And then what we call the propagation term, which should be familiar to us right now, e to the minus j kzz. So any guiding system, right, has e to the minus j kzz. Okay? Now, if kz is a real number, you usually call it beta, but it could be minus j alpha, in which case the wave is attenuating. But anyway, every wave, any guided wave has something that looks like this. Okay? Now, I've given you, I don't know if it's worth going over in class or not, but I've given a proof in Appendix A, if you want to read it, that basically all of the other 4 fields, EX, EY, HX, HY, come from these 2 if it's a guided wave. Now, in particular, as shown in Appendix A, if it's a guided wave, so in other words, E and H have this mathematical form here, then 4 components, EX, EY, HX, HY, can all be put in terms of EZ and HZ according to these equations here. Now, actually, in Appendix A, I only derived the first one, but if you understand the method in Appendix A and see how this one is derived, the other 3 work the same way. Okay? All right, so I think I'll just invite you to read that on your own if you're interested in that derivation, okay? But anyway, if you go through the appendix, then this is what's derived. So it's a really neat kind of a table. It shows that for a guided wave like this, you give me the 2 Z1s, EZ and HZ, I can get all 4 of the other ones, right? That's what this theorem is, if you want to call it that. Okay, now let's go back to what a TEM wave is. A TEM wave has no EZ and also no HZ, transverse electric and magnetic to Z. Okay, now something very interesting happens if you have a TEM wave that has no EZ and HZ. Let's go back to this table. Excuse me. Okay, now look at the table here a second. So everything on the left is put in terms of EZ and HZ on the right. Now, what would happen in this table if I said we have a wave that has no EZ and also no HZ? What would happen? No EZ, no HZ. Well, isn't the whole right-hand side 0? So what does that mean? You couldn't have any EX, EY, HX, HY? But we know if we have a coax, there is going to be E and H, right? We know that for sure. So what's going on? Okay, here's what has to happen. If I have EZ and H equals 0, but I still have these fields in the cross-sectional plane, right? If you look at the math, there's only one way that can happen mathematically. This denominator has to be 0. Does 0 over 0 have to be 0? No, not really, right? Okay, that's the only way you're going to get a non-trivial field on the left, though, right? Do you agree? So EZ and HZ are both 0. The only way you can get fields that are non-trivial, not 0, is if this thing, everywhere in the denominator is 0. So that's a simple proof then that for a wave called TEMZ, this must be 0. In other words, KZ is equal to K. And it works the other way around. If you already know that KZ is equal to K, then you can show that then it's TEMZ, that EZ and HZ are 0. Okay, so TEMZ means the same thing as saying that KZ must be equal to K. Okay. Now here's some of the most common examples of a TEMZ wave. Okay. Now, of course, a wave on a transmission line. Any transmission line has a TEMZ wave, whether it's a coax or twin lead or whatever. Again, here you have here's the E vector. Here's the H vector in the phi direction. The pointing vector, 1/2 E cross H conjugate, is going in the Z direction. That's where the directional power flow is. But in this cross-sectional plane, there's no E or H. The E and H vectors stay in the XY plane, right? It's a TEMZ field. Okay, and we already know that for a lossless transmission line, KZ is equal to K of the dielectric. Here's a plane wave that we just talked about recently. Again, it's TEMZ. Here's E in the X, for example, H in the Y, Neither one is a z component. Energy is pointing vectors in the z direction. And we already proved that for such a plane wave, kz is equal to k, right? We already know that. Even if k is complex, even if it is, kz is still equal to k. It's a property of any TEMZ wave that kz is equal to k. And these are the most two common cases, a plane wave or a lossless transmission line. Now, by the way, why do I say lossless transmission line? There's a footnote here. Okay. Now it turns out, okay, it's kind of a nuance, but for people like nuances, you can make the dielectric as lossy as you want, give me as high loss tangents as you want in the dielectric, and that won't change the fact that the transmission line wave is still TEMZ. Okay, just like a plane wave can be going through a lossy material like seawater, and it's still perfectly TEMZ, only has E, only has H, and KZ equal to K, even though it's complex. Now, if you take the conductors on like a coax or a transmission line, and you say they're not perfect conductors, but they're real practical copper or aluminum or something like that, and they're not perfect conductors, then theoretically, if you want to be a purist, the mode is not 100% TEMZ anymore. But people don't normally worry about that. By the way, quick little proof. How do I know that? How do I know that if you have a practical copper conductor, it can't be perfectly TEMZ? Well, let me just remind you Ohm's law. J is equal to sigma E, right? Okay. Our E is 1 over sigma times J. Now, remember, the current's going in the Z direction, plus or minus Z direction on the transmission line, right? So there's a strong current flowing in the conductors in the Z direction. Does that mean there has to be an EZ? Well, no, not if the conductivity is infinity, right? Because E is 1 over sigma J, and if sigma is infinity, I don't care what the current is, the E field is going to be 0, right? But if it's practical copper and the current going in the Z or minus Z direction, there will be a slight teeny tiny amount of E field in the Z direction inside the conductors. And that will probably leak through and cause a teeny, even more teeny tiny EZ field inside the Teflon. People don't worry about it, but I just want to point out, if you're a purist, then it's not 100% TEMZ once you put practical loss in the conductors, but people don't worry about it. So I'm just going to say it's fair enough to say that for any transmission line, it's a TEMZ wave. That's good enough for our purposes. Okay. All right. That makes sense? Okay. All right. Now, there's another result, and call it a theorem if you want. And I would say it's probably reasonable to maybe skip it one more time and let you just read it on your own if you want. Okay. So I've given you a second appendix called Appendix B. Okay. So Appendix A was that guided wave theorem. Okay. Appendix B is a simple proof, not very complicated. But anyway, it says that for any TEMZ wave or mode, and again, this could be a wave inside a coax, it could be a plane wave. For any TEMZ wave, this property has to be true. The E vector is minus eta of the material, square root of mu over epsilon, right? Unit vector Z cross H. Now, when I write this equation, I'm assuming that, remember, in this notes right here, I'm assuming that the wave is going in the Z direction, carrying power in the Z direction, right? Okay, that's why there's a Z hat here. So, and by the way, it actually even works for lossy medium. Eta could be complex. Doesn't even matter, right? But anyway, let's interpret what this equation means. Okay, so first of all, what it's going to mean is that the amplitude of E and eta, the amplitude of E and H are related by eta. We kind of already knew that. Amplitude of E is related to H by eta. But what does Z cross do for you? So it means that the E vector is always going to be perpendicular to the H vector, right? So if it's TEMZ, there's no EZ, there's no HZ. So E and H vectors stay in the cross-sectional plane. Like this is the cross-sectional plane, Z direction. They're going to stay in the plane of the blackboard, right? So E and H stay in the cross-sectional plane. And if you take a vector in the cross-sectional plane and take Z cross it, it's going to stay in the cross-sectional plane and just rotate by 90 degrees. So E and H vectors stay in the cross-sectional plane, and one is perpendicular to the other one, and the amplitudes are related by eta. Right? The simplest example is the plane wave, where you just have E in the X, H in the Y, and of course we already know EX over HY is eta, right? Now it's more complicated in the coax, because E is not in a fixed direction, H is not in a fixed direction, right? This is in unit vector row direction. This is called unit vector phi direction. E and H are getting much stronger as you approach the inner wire. It's like 1 over rho. So it's getting weaker as you go out. But still, at any point, E is perpendicular to H, and the ratio between E and H is eta. At any point in the cross section. So appendix B proves that this is true for any TEM mode, TEMZ mode. Okay, does that make sense? Any questions? Okay, good. We have about 5 minutes left or a little bit. Okay, so let me just get a running start. That's all we can do. But anyway, running start on notes 20. And of course, that'll be the main topic for Tuesday. Okay, the good old rectangular waveguide. Maybe on Tuesday I'll steal one from the lab and bring it with me. Okay. Okay, but here it is. A rectangular pipe. Again, could be filled with a material with epsilon, but 99% of the time in the real world they're filled with air. Okay. Okay. Now, just to keep it simple in this set of notes, I'm going to assume that the waveguide is made out of perfect conductor. Okay. Now, just like with the transmission line, the reason why you would want to really assume a real conductivity of the metal is if you want to calculate alpha and get the dB per meter loss. Okay, and that's what's done like in the microwave engineering class. We're not going to do it here. But for just calculating the fields and things like the cutoff frequency and everything, we don't have to worry about that. So I'm just going to assume it's a perfect conducting pipe. Okay, filled with an insulating material, which is usually going to be considered to be lossless too, just for simplicity, because I'm not worried about dB loss here. I'm just worried about the properties of the mode and the cutoff frequency. Okay. Now, one of the things, the most important thing to understand at the beginning is that because it's a hollow pipe of metal, there's two types of modes that can exist. One's called TMZ, one's called TMZ and one's called TEZ. Okay. Now, you cannot have in a hollow pipe of metal anything that looks like a transmission line mode, which like a coax mode or something. Remember, that's like a TEM mode. Okay, and I'm not giving a rigorous mathematical proof of it. Okay, but any TEM transmission line wave requires two conductors. They can be running side by side like a twin lead. One could be inside the other one like a coax. But you have to have two conductors. That's what a transmission line is. That's what a TEMZ wave is. Now, you can prove, although I'm not doing it here, that you'll never have a TEM wave propagating in a hollow pipe of metal like a rectangular waveguide. If you could hypothetically have a TEM wave in a hollow pipe of metal, then that means, like any other TEM wave, KZ would be equal to K, right? So if it's a hollow pipe of metal, I mean, that would be wonderful. If I have a hollow pipe of metal, I have a mode going down it where KZ is equal to K0. So just like a coax or just like a plane wave and go down to zero frequency, any frequency I want, that'd be wonderful. I could use this to propagate a 1 megahertz or 1 kilohertz wave, but sorry, unfortunately, that's not going to work, right? Because that cutoff frequency, right? So, but it turns out that you can have mathematically two independent types of waves, one called TM and one called TE, and it means the same thing as our plane wave terminology. Same kind of thing. So TMZ, there's no HZ, so only EZ, and TEZ, no EZ, so HZ only. Now, we can prove that these two exist, these two types of modes exist because we can solve for them. And we can solve for them independently, and that's what's actually done in appendices. Okay. Now, I'm not going to go, probably won't go through the appendices, or maybe I will, we'll see. But I mean, let's just talk a little bit about it. So TMZ mode, there's two types. TMZ mode means no HZ. So there's only one field in the Z direction, and that's called EZ. Now remember, microwave people like to work with those two, what I call the fundamental fields, EZ and HZ, because all the other four come from them, right? So microwave engineers like to work with EZ and HZ for any kind of a guiding wave structure. Okay. So anyway, so a TMZ wave has only EZ, and we've already derived this differential equation early in the semester. In fact, I did this for the plane waves, so go back and read that again if you want. It's called the Helmholtz equation. This is the equation that EX, EY, and EZ must obey. Same thing for HX, HY, and HZ. Okay, but I'd like to apply it to EZ and HZ because those are the two fundamental fields. Everything else comes from them. But remember, HZ is 0 for this kind of mode. So really, we're going to apply it to the field called EZ. So this is the differential equation called the Helmholtz equation that EZ inside of a rectangular waveguide obeys. In fact, it obeys it everywhere. But anyway, inside a rectangular waveguide, it has to obey that. But then I'm assuming a perfect boundary condition, PEC walls of the rectangular pipe. And remember, at a perfect conductor, what we call the tangential or the horizontal part of the E field has to vanish. Now, if you go back and look at the picture of the rectangular waveguide, so visualize Z coming out of the plane of the screen. EZ is going to be tangent to all four of the walls, right? So on the walls of the waveguide, EZ has to vanish. So that's what we call the boundary condition. EZ has to be 0 on all four walls. Now we assume that EZ has this mathematical form of a guided wave. Now KZ is the most important thing. That's the wave number. We don't know what it is. We want to know if we want to solve for it. Now it's true. I gave away the answer in the previous notes, but we want to see where that comes from, right? What is KZ? And that leads to cutoff frequency and all that good stuff. Now, anyway, so if you plug EZ into the Helmholtz equation, it looks like this. Okay, this is the del squared, Laplacian and rectangular coordinates. Now, what I do next is for the EZ right here, EZ here, 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 that's this. It can be written like this. So imagine taking this thing right here and plugging in where you see EZ. So that means what's going to happen. The Laplacian X and Y derivative works on this guy here. It operates on this. Okay, but what does Z derivative do? It just pulls down minus JKZ. And second derivative with respect to Z pulls it down twice. So we end up with an equation that looks like this. I guess I better stop here in a second. Okay, now let me just end by saying this. If I take this differential equation and I define something called KC squared, which by definition is K squared minus KZ squared, and that's a very important symbol. It's going to be called the cutoff wave number. We don't know that yet. But anyway, just a definition for right now. If I define KC squared to be this term, the differential equation comes down to be this. And this is something we can solve using the method of separation of variables, which is what's in Appendix A of the set of notes. Okay, so, but let's save that for next time. All right, but this is the fundamental setup of the math for solving for the modes inside the rectangular waveguide. All right, so we'll proceed on Tuesday. All right, thank you. Thanks so much.
Oh,